Hi everyone, this is the statistics practice test. It starts off with reading a couple charts. The bar graphs show trends in two areas of the United States economy. Refer to the graphs for problems 1 through 4. Number 1, over the 5-year period, what's the smallest difference approximately between exports and imports in the United States, and what year did it occur? So the smallest difference looks like it's approximately here, that this is the smallest difference in between it. And measuring that amount, if we come directly over and directly over, that's about 50, and it's in billions. So in 1991, it was about 50 billion was the smallest difference between imports and exports. Number 2, compare the differences between exports and imports. What's the trend? So it seems that in time, that the difference between them is decreasing. So it's getting closer and closer together in time. Or the difference is declining. Next one. During which year were the receipts from visitors in the U.S. about the same as the expenditures? So looking at the graphs, it looks like the receipts and expenditures were about the same in 1989. So we could see right here in 1989, they're the closest together. And then what we notice there is for the first time the receipts were above the expenditures. That's what happened in 1989. Number 4, compare the trends in balance of trade and U.S. tourism. How would you describe the relationship between the two? So noticing that in time here, U.S. tourism is increasing, and then also the balance of the trade is getting closer together. Next, from the frequency table shown below, construct a histogram and a frequency polygon. So there's a typo. It should be histogram. Okay, but in doing this, but a histogram is going to have frequency on the y-axis and the values on the x-axis. So this is the frequency. It looks like the frequency goes as high as 6. So as high as 6 going by ones. And then for the values, we have values between 58 and 60. So there's our values. And then for the first bar graph, or it's going to go up 2. And then it will go a frequency of 1. Then a frequency of 5. Then our frequency 67 to 69, another frequency of 5. Then a frequency of 6. And finally a frequency of 1. So there's a histogram. Then for the frequency polygon, we're going to also have a frequency that goes to 6. But now we're going to get the middle values for each of these. So the first group, 58 to 60, is going to be 59 is the middle value. The middle value between 61 and 63 is 62. Then 65, 68, 71, and 74. Okay, so then 59 would go to 2. 62 would go to 1. 65 would go to 5. 68 would go to 5. 71 would go to 6. And 74 drops down to 1. So this frequency polygon, I'll connect that. It starts from 0 up to there, and then goes. So that's the difference between the histogram and the frequency polygon. Number 6, the following data are exam scores achieved by students in a math class. Arrange the following data in a stem and leaf display with leaves ranked. Okay, so first step, we're going to check out the scores. It looks like the lowest is in the 30s, the highest is in the 90s. So the tens digits go 3 to 9. Okay, and now going through and rank in putting the data in. So 69, we'll just put the ones digit in 9, then 53, 49, 74, 68, 82. I'll order the leaves once I go through this. 66, 37, 58, 71, and now continuing 62, 60, 86, 67, 78, 59, 48, 93, 77, 83, 69, 92, 80, 75, 67, 69, 74, 45, 72, and 81. Now I can go back through and order these. All right, so I'm going to redraw this now. 3, 4, 5, 6, 7, 8, and 9. Now ordering. 985 is going to be 589. 389. Then ordering this group, I'll have 0, 2. Then we'll have a 6, 6, 7, 7, 8, 9, 9, 9. Then we'll have for row 7, we'll have a 1 and a 2, 4, 4. And then 5, 7, 8. Zero, 1, 2, 3, 6, and 2, 3. So here's my stem and leaf plot, and all the numbers are ordered. Using the same data from problem 6 to do the following, find the mean, the median, the mode, and the range. So to find the mean, I see there's 30 numbers, so I have to add up the 30 numbers and divide by 30. So doing so, the mean, adding up all the numbers and dividing by 30, I'll get 68.8. The mode, the most common number, is 69. To find the median, well, there's 30 numbers, so the median is going to be the average of the 15th and 16th number. So we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So it's halfway between 69 and 69, so it's 69. That's the median. And then the range is the largest number, 93, minus the smallest number, 37. So 93 minus 37 is 56 is our range. Next question, to get a C in history, non-done, must average a 75% on 4 tests. Score on the first 3 tests were 66, 79, and 61. What's the lowest score non-done can get on the last test and still receive a C? So 66 plus 79 plus 61 plus some last score x, all divided by the 4, that's the mean, the 4 scores, that has to equal a 75. So solving this equation, okay, I'm going to just add these 3 numbers together. 66 plus 79 plus 61 is 206. So we're going to get 206 plus x over 4 equals 75. Multiplying both sides by 4, I'll have 206 plus x equals 300. So subtracting 206 to both sides, we'll get x equals 94. So non-done needs a 94 on that last test in order to get a C, a 75% average. Next one, find the standard deviation of the following data rounding to the nearest tenth. We can use a calculator to get this answer. So the standard deviation, S sub x, when I use the calculator and type that into my list, equals 5.59, so it rounds to 5.6. Next question, the test scores of 15 students are shown below. Find the third decile. The third decile is equal to the 30th percentile. So we're looking for 30% of the 15 scores. So 0.3 multiplied by 15 is equal to 4.5. That means regardless of what that last decimal is, we're going to go up to the nearest next number. So 5. So we want the 5th term in the list. So looking at this list, the 5th term is 1, 2, 3, 4, 5. So 59. So 59 represents the third decile. At a local college, the mean GPA of a current student body is 2.76 with a standard deviation of 0.64. Find the GPA of a student with a z-score of 1.2. Okay, so our z formula is x minus x bar over s. So filling things into that formula, we'll have, we know the z-score, z is 1.2, so 1.2 equals x, the current score, we don't know that, minus the mean, which is 2.76, over standard deviation of 0.64. So solving this equation, cross multiply, we'll get x minus 2.76 equals 1.2 times 0.64, which is 0.768. adding 2.76 to that. The original score was 3.528. So rounding to the nearest hundredth would be 3.53. That's the current GPA. Next question. A machine produces bolts with a mean diameter of 0.30 inches. So that's the mean. And a standard deviation of 0.01 inch. So standard deviation is 0.01 inch. The diameters are approximately normally distributed. What's the probability that a randomly selected bolt will have a diameter greater than 0.32 inches? Okay, step one, let's find the z-score for 0.32 inches. So z equals x minus x bar over s. So x, then, this value is 0.32 minus the mean divided by the standard deviation. And that equals 2. So z equals 2. So now on a standard normal curve, then here's about z equal 2 right there. So we're looking for the area where the area is greater than there, right under here. So to figure this out, we can look up 2 on the table. And 2 on the table is about 0.475. Then we know that the area of an entire half of a curve, so this entire half, that entire area is about 0.5. Well, it is exactly 0.5 because it's half of the whole area under the normal curve, which is 1. So we can do our calculation as 0.5 minus 0.475. And that equals 0.025, which is equal to 2.5%. So what's the probability that a randomly selected bolt will have a diameter greater than 0.32 inches? 2.5% of the bolts will. I was actually just doing the problem with the empirical rule that for a standard deviation of 2, that 95%. So that's how I got 0.475. But looking at the table closer at 2, it says that it's exactly 0.4772. So the answer would actually be 0.5 minus 0.4772. That would be this area, 0.4772. And so then that would have an answer of 0.0228, or 2.3% rounded. Next question. The weights of a certain type of orange form a normal distribution with a mean weight of 15 ounces and a standard deviation of 3 ounces. Use the empirical rule to find the percent of oranges with weights as follows. So how many oranges have weights between 12 and 18 ounces? Well, the mean is 15. So that means that I'm either adding a standard deviation or subtracting a standard deviation, so plus or minus 3. So that's how we get between 12 and 18 ounces. So that's one standard deviation, and the empirical rule says that 68% of the oranges would be within one standard deviation. Next, more than 15 ounces, well, if it's a standard normal curve, then half of the oranges will be at lower than 15, half of the oranges will be above 15. So that's 50% will be more than 15 ounces, which is the mean. More than 18 ounces, well, you would have, I draw this out, so with the empirical rule, then 18, this area here, that area would be half of the 68, so that's 34%. So the whole area is 50%. So 50% minus 34% is going to be 16%. So 16% would be more than 18 ounces. And then next one is between 9 ounces and 12 ounces. So this would be between 2 standard deviations and 1 standard deviation. Okay, so graphing this, the mean is at 15, so 12 would be 1 standard deviation, and 9 would be another standard deviation. So we're looking for between 9 and 12. We're looking for this area right in here. So to figure that out, then we would have 34%, because that's half of 68%. So the empirical rule says 68% for 1 standard deviation, 2 is 95%, and 3 is 99.7%. So half of 95 divided by 2 is 47.5, just as half of 68 is 34. So this area, the whole area out here would be 47.5. And we can do 47.5 minus 34 and get 13.5%. So that's the number of oranges that would be between 9 ounces and 12 ounces. On a particular IQ test, scores are normally distributed with a mean of 100. So taking notes, the mean is 100 and the standard deviation is 10. Okay, so then the question is, find the probability that a single score will fall in each of the following intervals. So first one then would be less than 125. So let's first find the z-value that corresponds to 125. So this is x minus x bar over s. So this is 125 minus the mean of 100 divided by 10. That's this z-score. So that's 25 divided by 10, which is 2.5. Now, on a picture of this, this is going to be this normal curve here. So the z-score is at 2.5. And we're looking for less than that, the area that's less than that. So this would include all of this area here. So figuring out that total area, then from the center here to the left, that's all 0.5. That's half of the whole. Then figuring out the other portion, I could look up 2.5 on the table. So 2.5 on the table is 0.4938. So then adding that together, that's 99.38, which rounds to 99.4% chance that someone would have an IQ less than 125. The next one is, what's the probability that a person would have an IQ between 95 and 115? So first we have to find each of these corresponding z-scores. So for 95, z would be 95 minus 100 divided by the standard deviation 10. That's negative 5 divided by 10, which is negative 0.5. Then the other boundary is 115, so z would be 115 minus 100 divided by 10. That's 15 divided by 10, which is 1.5. So on our graph of a normal curve, then if approximately here is z equals 1.5, and approximately here z equals negative 0.5. So then we can look up 0.5 on the table, and 0.5 is 0.1915. And 1.5 on the table is 0.4332. So to get the whole area, we'll add that up. So 0.1915 plus 0.4332, and we get 0.6247. So that's about 62.5% chance that a randomly selected person would have an IQ between 95 and 115 given this data.